So integration, right, by parts. Right, one big topic like that. Then most of the work is done on the indefinite integral, the anti-derivative problems. Yeah. So let me bring you in a problem like this. Okay, we have an interval like this. How about x times e to the x, dx? Yeah. I mean, this integral now in these days, in these modern day, it has become common enough that you not want to Google it. It has the answer fields all over. But in the end, and think about it, for you guys learning from the beginning, I mean, learning from the origin, where these things come from, right? Then it's a whole idea right here. So there's a whole technique that people invented, and specifically can be used for this integral and so many other integrals. So this is what I'm doing, and I'm not talking about integration by parts or anything yet. Just let me show you the technique right here. Okay? Now, the one thing you notice, before the dx expression, right? Before the d expression here, right? Aside from that d expression, that's what I meant. Then your function here appears to be a product of some two functions, from two different families of functions. You guys are following? I mean, the x by itself right here is from the what? It's from the power function, right? X to the first power or something like that. See what I mean? And then the other one, aside from that x, then the other function here comes out from the exponential family, right? So basically, your entire function that you're trying to integrate here, that entire function, usually comes out as a product of some two other functions. Yeah, it's a product of some two other functions that come from two different families. Sounds good? So in that way, here's the work that we're doing. I'm going to actually, so because of that, I'm going to pick one of the two right here. I'm going to pick one of the two. And I actually will pick the first one right here, and I call that the function u. See what I'm saying, huh? Okay? It's just like I said, first thing I pointed out that there are two functions involved, right? There are two functions involved right here. I picked one. Right now it seems like the picking is just a choice. Now really, it's just a choice. You pick one of the two in your whole product, and then you call that your function u. Sounds good? And then that means after you pick that one, everything else remains, including the d expression right there. That's the way how I explain it to my students. Everything else aside from the one that you have picked, everything else in that product, including the d expression, you're gonna call it some other. I call it dv. So dv here is the differential of e to the x times dx. Yeah. Are we good with that? Right. So I separate it out. That's the idea about my part, right? One starting expression, but I appropriately separate it out into two separate parts. One part is a function u. The other part is a dv expression, like that. dv differential. Okay? But then essentially, see, you isolate out one of them, and everything else is the dv. Right. So now think about it this way: on your u that you have chosen right here, then yes, the u dx equals what? One, right? Or similarly, d u equals dx. Agree with that? Right? And so, trust me, at this point, you guys are fluent enough. At some point, I'm even going to go just from here, jump directly to there, and assuming that you guys already got that idea, right? On the other hand, think about it. See, you can play a little bit of trick right here. dv equals dx, dv as a differential, e to the x times dx right here. You can think about rearranging these. You got the dv over dx, right? Equals e to the x. You guys agree? So this is just a one hidden process that you keep in your mind to realize that, hey, wait a minute. So e to the x can be thought of as the derivative of some other v function. And so that means now v can actually be what? The antiderivative of e to the x. Agree? Okay. And then so, like I said, this step right here can be kept hidden in your mind. Okay? You can just understand that, hey, this expression really means the same thing as that. But that means what? Right from here, you can go v as another function. It's just simply a small antiderivative of that e to the x, which is easy to obtain. See what I'm saying now? Okay? And so, all of a sudden I produce I've chosen that only one element, and then I produce that other element, right? And then I additionally produce some two other elements again. By the way, this antiderivative, this little one here is easy, right? It's e to the x again. We can skip the plus c for now. We can skip the plus c for now, right? But now here's what I'm putting it together. All I need is the u that I have chosen. That's the u. I'm going to put that together with the v that I have found. The v that I have found after the little integral. This is the v right here. That's a product. Okay, so u times v, and I'm going to subtract. Okay, and now I'm going to set up another integral. Now I'm going to put the v right here, e to the x, okay, but multiply with the du. Du is really just dx, right? So I see this as the v right here, that dx came out with the du. Well, there you go. Okay, that's another way to see behind the scene. But now all of a sudden, here's what I realized. So the first term here is actually not an integral, it's already done that, right? So you've got x times e to the x. But with this new integral that I produced right here, think about disregarding all of these extra notation v and du, then you have an integral e to the x dx, which is very simple to handle. Well, I'm saying no. Okay? And so what does that make? All that now remains the same, x e to the x, but that's just minus e to the x. That's probably. Okay. Now let's check. I claim to you that now this is the antiderivative, one of the antiderivatives for that function. Okay? Papers and pencil. Take the derivative there. You see, if you land back into this, take the derivative of that x times e to the x minus e to the x again. That's the only way ever to check whether you have done whatever fancy technique that you've learned. That's the only way to check whether you have had the correct answer. Okay. It agrees, right? So that means now we have found it. So it's an antiderivative. So now at this point, this is where you put in that final c with them. So it's just the final c, it's just a matter of an extra constant term, right? So now my work here from the beginning, we wanted to find the antiderivative of x times e to the x as one function, right? It turns out the answer now turns out being x times e to the x minus e to the x plus c. So no, we found the work. I mean, we found the answer, right? But so now let's look at the work right here. What was in the work? See, in the work here, see, the first thing in the process, I made you realize, right? It's a product of some two other functions. So I put one function here as a u right here, right? And then the other guy right there, I call all of that is a dv. So your integral from the beginning. From the beginning, your integral from is recognized or is seen as a u dv. Saying that, right? So let me put it all together on this other board here. So from the start, I saw that problem. I was seeing my problem as some function u multiplied with the rest of that being a dv. And then I was doing the two columns thingies, right? And then I put together the elements. Now I can see that u times v is part of my answer. And minus another little work that came out from v du. See what I'm saying? Huh? This is one famous formula that actually gets you done with a lot of nice integration problems together. So we call this a formula to do integration by parts. And that's the work that happens right there in our problem. For you guys are being at the university math course level, right there, and at Calc 2 level, a formal calculus course. Let's have a little bit of a proof, because not too hard actually. I mean, normally I say a way for proof to keep you guys sticking with the more technical side, but at some point we want to know where the formula here came from. Think about it. In the end, u and v, they're all functions, right? Functions of x and all that. Hey, back into account one, if you got two functions, u times v as a product, how do you find the derivative? You know it. Product rule, come on.
Derivative of
There you go. It's u prime times okay.
And then plus multiplied by the root of
Easy, right? Okay. But now we we're blending in our integral idea here. Think about it this way. We can equally take the derivative of both, the antiderivative on both sides, right? Because if these two things are equal, see what I'm saying now? Then taking the antiderivative, right? I accidentally set the derivative, but when we, at this equation I'm talking about, when we take the antiderivative, we can do that equally on both sides. See what I'm saying now? Right? So, the rule for taking antiderivative is pretty much the same. The right-hand side here got two terms, so you have to split that into two separate integral works, right? One of them is on the u prime v right here, and the other one is on the u v prime. You guys follow it? Right? And this guy right here, it was on the left-hand side, it was a prime of the whole product. And taking the antiderivative, it's just the u times v, right? No prime. Just remember, this undoes the derivative. Agree with you on that? Okay. So I'm kind of leaving that hanging right now. Think about the u prime right here. The u prime as a differential. Okay. Well, u times v on the left-hand side, but the u prime here is a v of du, right? Because u prime here is the derivative of u in respect to x, or things like that. So we write that as a differential du right there, times v. And then the other guy, we didn't think of that v prime. The v prime right there is dv equivalent. So now what do I do here? I'm going to subtract that. Actually, sorry, I'm going to subtract this to the other side. This one right here. Now I'm looking at my integral a little backwards right here. U dv equals u times v minus v du. You guys see that there? And that's how we derive our famous integration by parts formula. It's whoever now is telling me that, hey, this is the reverse, the integration by parts formula is the reverse of the product rule. I agree totally. It was. Just rearrangement by parts. So I was also able to show the proof of where that formula came out from, right? So I'm just going to remind the formula, and then we're going to get to work on that. So we have the, how about I'll write it here. Now when you recognize your function, your integral that you're about to do can be written as a u dv right there, right? Then you can simply, the answer will come out being u times v minus another small integral that you will produce being v times du. Right? And I've demonstrated the idea of how it works, and we have proven that informally proven that formula, and then now we're gonna use that into some examples. But now let me still remind you guys a little more, so that so I brought in this problem, right? X times e to the x dx. So in the way how I explained this, so I chose. Well, the first thing is we recognize that this integral that we're doing here, the function, and by the way, now time to give you guys a couple new terminologies anyway. I will have a test for terminologies, okay? Terminologies is that I'm telling you guys that when I use it, you won't be shocked, okay? And you will understand what we're talking about. It's a way to properly communicate. So the whole problem is an integral problem, but the function that we're integrating, we call it is the integrand. Okay? So if you feel it's worth your attention to know right there, right? And it's how it's called right there, that just that function, right? Aside from the whole package symbol, the integral sign with the dx right here, that function is called the integrand. So the integrand we're looking at right here, the way how I have explained already, that you see it got x times the times e to the x. And so in my explanation from the demonstration you have seen that, you see the idea is it's a product of two families of functions, right? A product from two functions from two different families. So we can just simply pick one. So I picked u last time. See what I mean? Okay, and then once that we pick one here, that's why anytime that we pick something, that there's no right or wrong. See what I'm saying? No? Maybe there will be some good guidelines to help us successfully pick a good one, but there's not really a right or wrong. The idea now is that once for this integration by parts, once you have picked one, then the other one and everything else included in your integral becomes a dv. That's why for this problem, again, as a reminder, we got our function, right? X times e to the x dx. And of course, the integrand connected with that v expression here also as a product. That's why once you have isolated out and picked this as u and everything else here, right, in the remaining in the product is called a dv. And that's why we came to this. But so now, the challenge here is how do we pick a good working, okay? Is there a good guideline to pick a good working u so that we can treat the rest as a dv? Because right from the beginning, I mentioned, we picked. So I showed you that I picked this u right here for the x. But I could have also picked that. See what I'm saying now? Right? I could have picked that one as well. Right? So let's see what's bad and what's good. I mean, what's not working and what will be working. And so back from that beginning problem again, if I picked e to the x as your function u, right? Then the other one, the rest of them will be, the dv in x and times with the e to with the dx. Right? Remember that idea again? Once we have picked and isolated out our u function, then everything else, right, in the product, including the d expression, right, will become to dv. And so in that way, our u here will become, well, taking the derivative, so du will easily become e to the x. And now times the differential dx, right? Because du dx really was in a more step-by-step setting right here. Then right from here, du dx as a derivative equals e to the x. Okay? But then now at our level here, we understand this not only as a simple derivative, but now it's a differential. I mean, it's a ratio of the two differentials, du and the dx. So we can rearrange that dx to the other side. That's why I have the du, right? And in some near future, you guys will be fluent with me that I go directly into this differential form right here of our equation. Okay. So like I said, I could have picked that. No one's going to hurt you for that, right? No one's going to yell at you, hey, you picked the wrong u. There's no such thing as a wrong u. It's similar to the u substitution as well. But we use that for a different direction. And then so in that way, the v here, once the v is in x times dx, you can think of that. You can think of that as a dv, right? You can think of that as a dv over dx, right? It equals x, which is one derivative. So you can find v here by taking the antiderivative of the x, right? The x, see what I mean? And then that comes out with x squared, right, over 2. And so you can put together your, according to the integration by parts formula, and you can do the following. Well, u times v is a 1/2 x squared times e to the x, and minus, and then there's a v du, so it's 1/2 okay, x squared e to the x dx. See, the question again, did I make the problem simpler? Did I make the problem going easier? See, we got a new problem. We now got a new formula, and we learned that we can pick one and then treat the other one as a dv, whatever, but all serving one ultimate purpose. We got to make the problem easier in every step that we arrive. But obviously, here one sentence can tell me that this thing is not easier in the sense that hey, we're starting out with e to the x, right? Times x with the first power. See what I'm saying? No? And then we went with the integration by parts, and then we got into a fancy formula, and then we end up with another integral where it looks more complicated in the sense that the x here gets even higher power. See what I'm saying? No? Okay? And that's naturally telling me as a natural sense that the problem didn't go easier if I chose u from the beginning, if I chose u this way and treat the rest of the dv. So my point I'm trying to bring out for everyone is when you choose that u right there, there's a whole challenge, which could be a good u right there, right? Because we don't want to waste effort. I mean, we don't want to hopelessly waste a lot of our time looking for one u and then go all the way down, and then all of a sudden we realize we're stuck, and then go back to that beginning and try another u. We don't want to do that. I mean, in the substitution method, right there, choosing a wrong u, it's already cost you a lot, right? I mean, choosing a non-working u, it already cost you a lot. And for this thing right here, if you chose a non-working view. It's not a wrong one, but if it's not a working well one, right, it's even cost you a lot more. See what I'm saying? No? So for this, I have to tell you some good news, but there are also some minor bad news. Okay, there are some good guidelines that, but only the minor bad news is it's only working about 90% of time. Okay, it still doesn't guarantee 100% of time to work. Okay, so the remaining 10% of time you're still going to have to search on your own and try on error. Okay, so the guideline here is people use this. There are so many ways people are writing it out there. People writing it this way. Right? This is the way how I learned it at first. But in these modern day, people also call that the alternative. You may see people call that the Liate. That's one way of calling that. But I learned from my professor, my favorite professor back then. It's called Lipton. Okay, but it's just a shorthand writing of okay. And when you read this guideline, when you read from the left to the right, okay, the L letter here stands for the logarithm family. Like the natural log, the log base 10, the log base 2, all of the logarithm family. Okay, anything that you recognize being involved or deals with log, right? That's we consider it as a log family. Sound good? And then reading from the left to the right, so after the logarithm, the I right here is specifically stands for the inverse, but inverse, what inverse? Trig. Okay? Like the sine inverse, the cosine inverse, the tangent inverse, and all that. So not all inverses out there. It's only they meant to be the inverse trig. And then the A and the P here being used loosely, but it means those power functions. Okay? Like say x squared, x to the first power, x to the 10th power, or square roots. Okay? Or cube roots, we get those roots, and those are all considered as a power function. That's why I write it as powers. Or we look at that. Okay? And then we got the trig function. These are different families of functions that you have seen throughout your pre-calculus courses. Okay? And then the last one here is the exponential. So a to the x, 2 to the x, e to the x, and all that. Okay? And so what's up with that? So again, when you're reading this guideline, the letters arranging from the left to the right right here, that means whichever the family that comes on the further left, right? If you see a product, that's why back to this. We got powers, you guys see that there? You got exponential, right? And your integrand here is a function of, as a product of those two functions from those two different families. And so now you're looking at up on that. This chart is the function from the left to the right, the power function, right, comes before the exponential, so it has higher priority to be chosen. It's just indicating a guideline to pick which one is the higher priority to choose first. I'm always saying C is a higher priority. That's why there's still a small chance that it fails. Okay? Good enough with that so far? And so that was the reason why that's what led me into choosing u equals the power function. Okay? U equals x. Okay. Are we good? And then once you have chosen your u, right, then the dv comes out just like how I have explained. Everything else aside from that factor, right, in your products, the e to the x, including the dx, that goes into your other part. Right? And so that's why, like I said, repeating that process. Now we're looking at the u equals x, dx, and your other one here is the v equals just e to the x. And then all that we did our work, and we already saw that work earlier. Right? So this is I see it's a good guideline. It's been working quite well as well. But I have already also seen points and instances where it failed, where I still got to spend some time searching for a working one. Right? Pretty costly with that. So this guideline right here is only as a guideline. It's not a rule of hey, you got to always stick with that. Right? It's just a rule that helps you get the problem done about 90% of the time, or a little bit less. All right, so we got that Liate or the Lipton, whichever way, however way you want to call it. All right, so now in that way, let's swing it over to the other board. Let's get some problem done right here. So we want to practice our skill. We want to see the more examples we get, the better it is. So let's call it example 1 right here. So about x squared minus cosine of x. Right. So for this function, just like that, the scheme I was pointing out here, the way how I'm seeing it, sort of like on Scratchword here. Shortly, I'm going to have to erase that. See, your integrand, you got x squared times the product, right, with the cosine of x. That's what I would. So as far as that product of the two families of functions, we got the power family, right? And then we got another function that came from the trig family right here. So now we're going to look right into that chart here. Right? So the power function belongs here from the left to the right, right? And then the trig function comes right after that. So who has higher priority? The power function has higher priority. So that just tells us that, hey, we should, that's why we just should, but there's no guarantee, right? We should try out first to have u equals that whole power right there. And once we have isolated out the u right here, then I'm going to see thing on the other side. Everything else, right? Everything else in this product, including the dx right here, is going to be considered as a dv. Now my dv is a cosine of x times dx. Okay, good? All right. Now, once you have had that, right? Okay, so this is power, this is trig. There you go. Now in that way, let's work with that. So that's how it is. Once you have chosen your u and your dv's, right? Then the work that you have done after will matter. See what I'm saying? So if you take the derivative here incorrectly, that's where you will get your work done incorrectly, right? Now du here equals 2x times dx. You guys agree? So technically, du dx, right, equals 2x, but we rearrange that dx as a differential. And in the same way right here, so now think of this dv equals cosine of x dx. Think of that as, hey, the derivative dv dx equals cosine, right? So finding v right here, which is just a matter of integrating that cosine of x dx. All good? Okay. And then sooner or later, you guys are going to be all fluent to the point that I don't even need to write this little step again. So cosine of x. So we found v. We know we chose u, and then consequently we found the u, and we found v again. All that. All right. So now let's put the pieces together. See how things work out. Now this thing right here, this function this integral according to the integration by parts formula, we meet u times v. U is x squared, v times v is sine of x. That's good. And then we're going to have minus, right? We're going to produce a minus. Now our function here is a v du. So v is here, and du is a 2x. So 2x sine of x, right? And then of course with another dx. That's the 2x dx together with the v we get, right? That's why we have the 2x sine of x dx. Right? Admittedly, the problem didn't seem any less the complicated, but at least what brings a good sign of hope for you, I'm just saying a good sign of hope, is that we still got a product of two families of functions, right? But this thing here on the right side already reduced the power, see what I'm saying? Huh? So something rings a bell that it actually got a little easier already. So the idea now is that we can go ahead and apply the integration by parts one more time right on this step here, see what I'm saying? Huh? We can always apply that as many times as you want until it gets to work, right? All right. So that's first step right here with the integration by parts. You get to that. Now I need to erase that to make some space, right? So just like that, more practice for everyone here. So let's choose u and dv for our current integral here. Now again, I'm labeling it this 2. And why do I put I can go ahead and put the 2 here in front of the integral and just make that x dx just like that. Of that. Okay? And so it's a product again, right, of a power function. That's power, right? And that's a trig function again. Get that? now I can go u equals x. That makes du consequently equals dx. dv can be chosen to be the sine of x. dx, right? Everything else is that. And so that means v has to be the integral of sine of x dx. It's v equals to negative cosine of x. And the plus c can be also skipped here, right? Because these little integrals are just small enough. Well, I'm saying so that we can skip the plus c, and we're going to put the final plus c at the end once you found the overall antiderivative. Right? So now here's one more step, and use parentheses. So in case that you really have to go through like many steps to apply your integration by parts, make sure you use parentheses carefully. So this is what I mean here. The first term is pretty much done. So I'm leaving that x squared times sine of x. Are we good? And I'm subtracting 2, but whatever result here, that's the result for this integral about to be worked out, right? So I have to put that in parentheses because the minus 2 will multiply with all that. See what I mean? Okay. And so here's how I'm seeing it. Okay. So now I have according to the integration by parts, this integral here will give me minus x times the cosine of x. Does everybody agree? And then I'm subtracting according to the integration by parts formula, right? I have another integral. Seems like we keep looping into more integrals, but if it works, at some point it will open up a way out for us right here. But now v du right here, so v is a negative cosine of x, and du is just simply that dx we have found right here. Are we good with that? So it was 2 levels, right, of integration by parts work. Okay. And so now I'm still going to carefully use the parentheses here. X squared times sine of x plus term outside the parentheses stays the same. Now that sign in the parentheses here, that negative sign together with that negative sign making it negative, right? So I have making it positive. So minus 2 in parentheses minus x cosine x plus an integral, right? Or cosine of x. Are we good with that still? Okay. I'm still moving extremely slow so that you guys can catch the steps and understand the fundamentals. And once we add a few more problems, we can start picking up the pace here. So now x squared sine of x. I can go ahead and distribute that minus 2, making it a plus 2x cosine of x. And notice now we got one more term being done, right? And then now I'm going to think about subtract 2 integral of cosine of x. X. Good. So we still got hung up with one more integral, right? One more little integral. But now question yourself, do you actually need to use another integration by parts for this thing? No, it's just one of those ordinary ones. What's the antiderivative for cosine of x? Sine of x. That's it, right? Now that one's so easily done. Easily done. So x squared is plus term times sine of x. That's a plus term. Plus, I've got 2x times the cosine of x, right? You get that? And then minus 2 sine of x. And now this is a good place to put in your final plus c. You know what I mean? That's what right? But actually, I was a little rushing. Why don't you guys, even though I already did that, but why don't you guys take the derivative on this final antiderivative right here to ensure that we actually found the correct antiderivative. Remember our starting function was the x squared times cosine of x, right? So I want to make sure that this is the real antiderivative. So why don't you guys do what? Take the derivative of this here to ensure that we really gonna land back into this integrand. Are you good with me on that? Right. So take your time doing that and verify that result for me. It's a live survival skill, and when you do your indefinite integral work. Thank you. Yeah. So of course, it's not part of. It's not a required part to be included. But you guys should always, be extra cautious, right? Double check your final answer here, because this kind of work here is starting to get you into a lot of things involving. We easily make mistakes. Okay, we make mistakes very easily with that. So double check your work. Okay. All right. So what about another problem? And then the entire example 1, I purposely bring in those problems where You guys can do that easily where it stay pretty focused with the Lyautey scheme with that Lipton guideline. And then I'm going to also show you there's some problems that you're going to need to shop around, right? So let's call that part B of the example. Okay. Let's find that antiderivative. Again, our iterand here is x, right? Times the natural log of x. And I purposely put you guys over here so that the Lyautey scheme is right here, that Lipton. So as far as the products, we got two families of functions, right? Multiplied together, the power function is here. You get that? Power, right? And then what you have here is the logarithm. You get that? So clearly there's a, so according to this guideline, right? The logarithm becomes a higher priority because it's the first one from the left, right? And keep going down the descendantly. So that means that we should choose, it's just a suggestion, right? We should choose the logarithm to be the first, the higher priority one to be chosen as your u again, right? And so in that way, I'm going to take that idea and bring that into the actual problem again. U equals natural log of x. Okay? And then from there, everything else, including the dx, right? So I have dv equals x times dx. What I'm saying, huh? So this logarithm here, when you take the derivative, you got du, the derivative of that. What is that equal to? Calculus 1 stuff right here. 1 over x, very good. 1 over x. And here we write it in a differential form, right? The derivative times the dx again. And so now with this one right here, think about v will be the integral, right, of x dx, which should be also easy enough until you want to breach, right? So go ahead and find that little indefinite integral again. And we'll need the plus c here.
Oh, for v? Oh, that's just 1/2 x squared.
There you go. That's 1/2 x squared. That's all we need for now, right? So now here we are for now for our next step here. So into the integration by parts formula, we have 1/2, right? That I should write the x squared plus. So x squared times the natural log of x. But that's u times v again, right? And then we're subtracting. So now v du. So v is 1/2 x squared. vu is this. So we have a 1/2 x squared times a 1 over x dx. Okay? So in the next step, I'm just going to clear out a couple common factors right here. So 1/2 to be brought in front. X squared cancel with the x, making it x dx. We good? So this integral here, did it get simpler? This little integral that we produced for ourselves. Did it get simpler? It did, right? So now the answer comes out easily. First term is 1/2 x squared natural log of x. Now we're looking at the minus, right? 1/4. You guys following? X squared. This is the place where we're putting in that plus c. Okay. Again, please quickly double check your work right here, because I may make a mistake all over, right? I may make a mistake along the way. Who knows? This example right here. Let's call it example 2. So this one here has its own specialty. Let's look at something like this: e to the x times the cosine of x. Yeah. Point out for you, the Lyautey scheme is still going to work pretty well with this. Your integrand right here. You got exponential, agree? Right? Exponential, and you got trig, right? So now you guys can rely on this scheme again. Tell me which one should we choose first. We choose the trig, right? Right. And so, but that's just a suggestion. But let's go with that suggestion. We're gonna go with u equals cosine of x. Right? And then on the other hand, we got v equals dx, dx. Everything else is aside from what we have isolated out as our u. Okay, so here's our dv actually. So the derivative of u, but as in terms of the differential form, so we got du equals the derivative of that is a negative sine of x, right? And then our differential of dx. So du equals minus sine of x times dx. And so the v here, it's indicating that to find v, you're going to have to go ahead and take the antiderivative of that, right? Take the indefinite integral of that. So v equals just x. We don't have to worry about a plus c in this case. So now we're going to put the pieces together. So we're looking at e to the x times cosine of x. Right? We're subtracting. Then v du, v is here, du is here. You're looking at minus and then e to the x times another, but here it's minus e to the sine of x dx. Double check me before I go on too far. Did I put the pieces in together correctly? Well, there was a minus sine of x dx, right? That's our du. That's our v is e to the x, right here. Look good? So we have seen a situation similar to this. That's likely we're going to need to do another level, right, of integration by parts. But let's just rewrite it e to the x cosine of x, right? Plus the integral of e to the x sine of x. Are we good? Okay. And so now I'm going to erase the work right here. And I'm still going to rely into that scheme, that guideline right there for the arcade. So right now, e to the x is one family, right? E product is sine of x. The trig family, the exponential family. So let's go with, as a higher priority, I'm going to choose u equals to sine of x. And so now, dv equals e to the x dx. Yeah, very similar to the earlier one. Okay. Right. And now, why don't you guys rely on your own sense, your own natural sense to tell me that when you have gotten to this point here, did the integral get any easier?
No.
Not really, right? Because at first we got an exponential with a trig, and here we ended up with another exponential with trig, right? So the amount of, I mean, we're glad that the amount of the complicatedness didn't get higher, but it's still just about the same, right? The amount of complexity is still.
See, do it again.
Yeah, so we still want to do it again, right? So just like that similar experience we've had. So here I'm looking at du equals a cosine of x dx. The v here is the integral for e to the x, and then v will be just dx again. Are we good with that right there? Okay. And so now in my next step, the integration by parts tells me I can do this. dx cosine of x. Came out from the term that we're already done. So with this thing right here, plus let's leave parentheses here to put the whatever the work for integration by parts just on that integral inside of the parentheses here. So it's going to be e to the x times sine of x. Are we good? Okay. Minus, and now we got e to the x. Okay, the v times du, e to the x times cosine of x. Yeah. Okay. And then we're breaking the parentheses out. So we're looking at something like this. E to the x times cosine of x plus e to the x times sine of x. You guys following? Minus, and then there's the e to the x times the cosine of x. X. We're going to start putting it now. Our palm right now, our thumbs right now change thinking. Something weird going on here? What have we arrived at? Yeah, we end back with that beginning thing again, right? So here's the thing. Think of it this way. Now let me erase this. The good news here is that we don't have to. We can depart from the integration by parts. We can depart from that. Because if you keep doing that, you're going to run into the same loop over and over again. See what I'm saying? So the plan here is that right now, in the way how I see it, all this here equals that on the left-hand side, right? Let's rewrite it this way. The integral dx from the beginning currently equals to, right? Currently equals to the e to the x cosine of x plus e x, right? Minus, right, the integral from e to the x cosine of x dx. You guys agree? That's just how we're writing it, right? So this is the integral from the beginning, and currently it has we have proven that it equals to all this. So we have that equality just fine, right? So now seeing this as an equality, seeing this as an equation, why don't you, and it's got a negative sign right here. Okay? So why don't we add this to the other side? See what I'm saying now? I'm adding this negative sign term right here to the other side. Looking at what? My next step here, importantly, turns out to be 2 integral of e to the x cosine of x dx, because I added that to the other side. You guys believe that? So on the right-hand side, everything I have left behind here is just e to the x cosine of x plus e to the x sine of x. You guys agree with that still? It's just the algebra, the algebra argument of that, right? Alright, and now let me write it on this board right here. So currently we got into 2 times the integral of e to the x cosine of x dx to equal with e to the x cosine of x plus e to the x sine of x. So that's where we're at right now. Okay. And so what do we do next? We're just going to simply divide both sides by 2 right here. Look at what I brought for myself. The integral of e to the x times cosine of x dx will equal to what? E to the x cosine of x plus e to the x sine of x all over 2. We're done. What's equal? That's how it's done. Right? So we can do things like that as well. A little more experience to put into your learning pocket, right? Carry around. You know what I'm saying? When integral going hopeless and keep looping around, right? That's what we can do with that. If we recognize like terms from both sides of your integral equation with that, right? You can go ahead and rearrange the terms around and making it something like that. So the shocking step, see, when I learned that, at first I was as shocked as any one of you guys here is anyway. So just like that, we right from this here, the good thing is we got that minus sign, right? We added to the other side, making it a 2, right, of that integral, and then equals to all this. So all of a sudden we feel we're done. Dividing both sides of that 2. Okay? Alright, so for that problem, it stands on its own right there. Let's look at another one for you. Let's call it example 3. Right. Now, we have never done this any time prior to this, but now we can actually do this. You see, finding the derivative for natural log of x is easy, but finding the antiderivative of natural log, okay, let's find out. If you guys take notes closely every day from our beginning days until now, you can recognize that we've never formally learned how to take the antiderivative of natural log. You know what I'm saying? Okay, now it's here. So think about this problem, and this is the scary part right here. I've been talking about there's a product of 2 functions, right? And one is from the log family, or one from one family, and then the other function is from another family. If this function here, this thing here, there's only one function, right? It's not even a product of 2 things. See what I'm saying? No? So you can see it like this. You can let u equals, and this is one of the special ones. You can just let u equals straight into that. You only want that. Good. And so once you've decided u equals this, only one, right? Everything else meaning what? Just the dx is what's remains, right? Equals to dv. See what I'm saying? No? So now in that way right here, then we have what? Here du equals 1 over x dx. It's a differential form, right? This one here goes v equals x. Are we good? Okay. So now let's put it together. Integration by part formula, say the first term is multiplying u and v. So we've got x times the natural log of x. And we're subtracting according to the integration by parts formula. We're looking at v times du, right? V times du right here. So v is x, but du is 1 over x dx. You guys see that? Okay. So let's see how cool it's going to get. Okay. X, natural log of x is here, minus this integral we have produced. It's going to become just simply 1 dx, right? Or just dx. And so what's that easy one with them? First term is here still. It's minus just now. X, right? Because the integral for that is just simply x. Now we've got plus c. And yes, time is running short for me, but you guys on your own time at home, right? Outside of class, can go ahead and verify that we have come to the correct final answer. See what I'm saying then?